Yeah, so good afternoon, one and all. Um, um, so my name is Om Prakash. So I'm an alumni of Amrita University. I completed BTech Computer Science in Amrita in the year 2013. So a quick introduction or a background about me. So once I completed BTech in Amrita, I joined a company called Mu Sigma, where I was a decision scientist working in data analytics and consulting, etc., for around 3.5 years. From after which I moved to a bank called HSBC, and then switched over to multiple banks. And now I'm currently working in a bank called Synchrony Financial. I'm into credit risk analytics. So Senthil Kumar sir had asked me to deliver this session on data analysis and interpretation, and he had asked me to cover. He had given me a few topics and had asked me to cover those things with specific examples as such. In the interest of time, let's probably get started with that directly. So I'm sharing the screen. Let me know if you are able to see. Just a second. I hope the screen is visible now.
Yes, yes, it's visible.
Yes, sir.
Okay, okay, sure. Okay, we'll get started with some with the agenda. So today we'll start with the types of data, different data summarization, distributions, etc., which are useful to understand the concept of hypothesis testing. Sir had asked me to cover hypothesis testing along with other things like data modeling steps involved in data modeling, various types of tests like parametric and non-parametric tests, etc. But since hypothesis testing is a fairly comprehensive topic which requires good amount of time, I thought today we'll cover hypothesis testing alone and keep the rest of things for the next session, which is happening tomorrow. So we'll quickly have a we'll have a quick introduction on the other things like type of data, etc., and spend more time on the hypothesis testing with a couple of examples. Please feel free to stop me anytime in case of any questions. So types of data, as you all would know, we have two different types, qualitative and quantitative. In case of qualitative, we have two different types of data, nominal and ordinal. In case of nominal, it's a set of categorical values with no emphasis on the order of its existence. So for example, gender, male, female. Now whether we um, write male, female, or female, male, it doesn't matter. So these things where the order does not matter, they are called nominal values. And in case of ordinal, they are again discrete, and they are again not quantitative, but the sequence matters in case of ordinal. So things like um, grades that we get in exam results, or the number that we give on a scale of 1 to 10 as a feedback or rating, etc. So here, although the values don't have any quantitative value on its face value, on a relative scale, the order does matter. So these are ordinal numbers, ordinal values. Now coming to quantitative, as you all know, we have discrete and continuous. Discrete is the set of data which can be counted and cannot be broken into parts. So things like number of students or number of cities, etc. Uh, the possible values for discrete data is the set of integers or set of whole numbers, etc. And fractions or decimals are uh, out of scope in case of discrete. Whereas in case of continuous, the data could be divided into smaller levels, and the variable could take any value between the set of ranges. Like if the range is 1 to 2, in case of discrete it could either be 1 or 2 only, whereas in case of continuous it could take any value between 1 and 2 as well. Basically fractions and decimals are also in scope in case of continuous, example being temperature, height, etc. um, Now in case of data summarization, uh, we could summarize the data in a wide variety of types. Um, in case of qualitative, for example, we could summarize the data in terms of histograms, pie charts, etc., so on and so forth. But here in today's session, let's focus more only on the quantitative data, um, so that we could, it could serve as a good platform to understand the hypothesis testing. So in case of continuous, even in quantitative, let's have more focus on the continuous part. So given a set of data, there are broadly two types of summarization. The first set being centrality, so which talks about what is the in literal meaning, what is the middle point among the data points present in the data set. It could be calculated in three different ways: mean, median, or mode, where mean is the average of all the data points. Median is the middle point of the middle point after we sort the data in either ascending or descending order. So if we have 100 rows in a particular data, let us take age for example. Let us once we sort the ages in ascending or the descending order, whatever is the 50th value, that happens to be that is denoted as median. Whereas in case of mode, the the number which repeats the most, or the number with the highest frequency, that is mode. Now again, for hypothesis testing, median and compared to median and mode, mean is more relevant in case of hypothesis testing. Now dispersion, coming to dispersion, it is a measure of how far the data is from the mean, like are the data points very close to the mean, or are they away from the mean, etc. So that is quantified or measured by metrics like variance, standard deviation, etc., which all comes under dispersion. Like variance and standard deviation are almost they both measure the same, which is how far each data point is um, from the mean, and the average of all those things, all those distances from the mean, gives us the variance, and the square root of that is the standard deviation. So if we have 100 data points, and the mean of those 100 is n, then variance is nothing but the average of distance between each of those 100 points, x1 to x100, minus n divided by minus mean mu or whatever, divided by n, which is the number of value, number of rows. That gives us the variance, and the square root of that is standard deviation. Range is nothing but the highest value minus lowest value among the 100 data points. Now skewness and kurtosis are again measures of how far or how the different data points are populated uh, with respect to the mean. Now again, we'll move on from here without spending much time on skewness and kurtosis, since anyway the mean and standard deviation are going to be very useful in most of the hypothesis testing cases. Now, once the next concept which is necessary for hypothesis testing is about distributions of data. Now, what does distribution mean? It means, the distribution gives the an exhaustive set of outcome each random variable or a random event could have. So let's take an event of tossing a coin. So the distribution of this event of tossing the coin will have two elements in it, which are head and tail. So for if the event is tossing the coin, the probability distribution is head and tail. Now as a part of this probability distribution, we also get the probabilities of different uh, possible outcomes. So in this case of tossing the coins, while head and tail are the possible outcomes, the probability of getting a head and getting a tail are also important. In this case, it is 1 by 2 and 1 by 2. Now, if we consider rolling a dice as the event, the distribution would have 6 possible events, 1, 2, 3, 4, 5, and 6. And the probability of getting any of those is 1 by 6, 1 by 6, 1 by 6, and so on. Now, based on how the data is distributed, we have multiple distributions. The key ones are binomial, normal, uniform, Poisson, etc. Now, binomial distribution is one in which uh, uh, I mean the it covers those events which have only two possibilities. For example, tossing a coin, and a limited uh, number of trials. So let's say 100 trials, or 50 times a coin is tossed, 60 times a coin is tossed, etc. In those scenarios, the outcomes of those scenarios would form binomial distribution. We will quickly see the other distributions, and then come back to how to calculate the probability of an event in each of these distributions. Uh, in case of uniform, it's like an example of a uniform distribution is rolling dice. So by definition, in case of uniform distribution, the probability of each of the possibility in that sample space, in that distribution should be equal. So in case of rolling a dice, for example, each of the outcomes 1, 2, 3, 4, 5, and 6 has equal probability. So such outcomes are called form uniform distribution. And in case of Poisson, again, those things like Poisson is again another discrete distribution, where it is again useful for only small population. So things like number of um, cars that pass through a traffic signal, or number of accidents that happen in a junction, etc. Those come under Poisson distribution. Now, each of these distributions will have its own parameters like mean, standard deviation, etc., and and formulae to calculate a probability of an event happening. Let's not get into each of them. That's probably not the scope of this session. Let us get into one of these. For example, let's take binomial distribution as an example, and see, or let us come back to it. But let us move on to hypothesis testing, and we will come back to these distributions when we see examples for hypothesis testing. Now, hypothesis testing is a very broad space which has multiple applications. We'll see it conceptually what it is, etc. first, and then have a couple of examples, during which time we'll come back to the distributions to get the probabilities. So in case of hypothesis testing, we first define something called null hypothesis, and we try to we challenge it with alternate hypothesis and try to find out uh, whether the null hypothesis holds or the null hypothesis needs to be rejected. So until the null hypothesis is rejected, it's assumed that alternative hypothesis is alternate hypothesis holds. So in talking in terms of legal parlance, so we usually call it as innocent until proven guilty, right? So that's the state. So null hypothesis is like the steady state where it is um, it is the steady state like innocent. The alternate hypothesis is the opposite of that, opposite of innocent being guilty. Now unless we prove that alternate hypothesis, the null hypothesis remains true. So unless proven guilty, the person is going to be called innocent. Now to do we are talking all of this in terms of probabilities. There is nothing true or false as such. It's a probability game, so it's between 0 and 1. It's not 0 or 1, but it is something between 0 and 1. So because we are talking about probabilities, we also need to uh, talk about how confident are we in telling whatever we are telling. So that is where the significance level comes into picture. So probably we'll get into a few examples. Um, so that would help in understanding this hypothesis testing better. So let us take the example of rolling the or example of tossing a coin. So as we all know, tossing a coin has two outcomes, head or tail. Let's assume that we are tossing a coin 20 times, and or let us say 50 times, and the outcome that we see is that um, 45 times the coin had given heads, and remaining 5 times alone it had given tails. Now we need to check whether the coin is fair coin or unfair coin, or biased coin or unbiased coin. So for a coin to be fair, um, the probability of head and tail should be equal. But here what we see is that the coin has got 45 heads and 5 tails. From the looks of it, it seems like it's not a fair coin, because more than 90, I mean almost 90% of the times we have got a head, whereas only 10% of the time we have got a tail. But we should prove it statistically, which is where this hypothesis testing comes into picture. So when we roll it 100 times, I mean when we toss the coin 100% of times, it is very unlikely that we will get exactly 50 heads and 50 tails. Sometimes we could probably get 55 head and 45 tails, or 45 heads and 55 tails, etc. as well, even if it is a fair coin. But in this case, we have got 95 heads and 5 tails. Now we need to actually statistically prove or disprove that this outcome of 95 I'm sorry 45 heads and 5 tails is not happening by chance, but it's happening because the coin is not an unbiased coin. I mean, it's not a fair coin. So that's the exercise that we are talking about. Now, in this case, the null hypothesis should be as in the case of innocent until guilty. Here, until we prove that this coin is not an unbiased coin, we cannot state that it is unbiased. So we will go with the null hypothesis that the coin is uh, fair, fair or unbiased. So let me open Excel. Okay, in this case, null hypothesis is coin is fair. Alternate hypothesis, this coin is not fair. Now, if we want to prove that coin is fair or not fair, uh, to do that, the data points that we have are 50 trials of tossing the coin, in which we have got head 45 times and the tail uh, 5 times. Now we need to calculate something called p-value in hypothesis testing. So this p-value tells the probability of the alternate hypothesis to happen, assuming that the null hypothesis is true. So in this case, the null hypothesis is coin is fair. So p-value is nothing but probability of um, 5 tails or lesser even null hypothesis is true, which is coin is fair. Now we are getting 5 tiles, but we could we need to get the probability of it being even smaller as well. Or in other words, we are getting 45 heads. Probability of getting lesser than for anything lesser than 45 is what we are trying to calculate. So let us do this calculation. Just give me a minute. Yeah, sorry. So here, although it gives the same meaning, we'll just rephrase it. Probability of getting um, 45 heads or more given the coin is fair. So in our observation, we saw that we have got 45 coins, but what we are trying to prove is the or check is whether the coin is fair or not. So now if the coin gives more than 45, which is the observed value, then anyway the coin is bound to be not fair. I mean, it's all the more reason to believe that the coin is not fair. So instead of just seeing any number of heads more than 45 up to 50, anyway it's not possible to get more than 50 heads because the number of trials itself is 50 alone. So now 45 onwards, so 45 46, 47, 48, 49, and 50. So these are the 6 different possibilities for which we are trying to get the probability and adding them up, because in a given trial of 50 we could get either 45 heads or 46 heads or 47 heads or so on. So all these are independent events, because we are talking about independent trials of 50 tosses each. So the sum of all these would give the total probability of getting 45 heads or more, assuming that the coin is fair. Now, now let's go back to the distribution. I hope you are able to see the Excel. I came out of the screen slide share.
Yes, sir, it is visible.
Okay, sure. So coin tossing of a coin, as I said, comes under binomial distribution. So in case of binomial distribution, let's now see what is the formula to get the probability of an event happening. So in case of binomial event, the probability is NCX p to the power x and q to the power, I mean p to the power nc or p to the power x into q to the power 1 minus x, n minus x, where n is the number of trials, in which case, in this case, which is 50, or is what we are getting here, I mean 45, 46, and so on, whatever is the outcome. P is the probability of the event. In this case, it is a head. Probability of head is P, and Q is the probability of it not being head, which is 1 minus P, which is a probability of tails. Power x, x here is 45, and n minus x is 50 minus x, which is in this case 5, next case 4, and so on. So let us get this probability for each of these values. So 50, let us fix 50. This. So this is x, this is n minus x. So we could, and the probability of head is 0.5, probability of tail is again 0.5. So probability is equal to, you could use a function called combine to get the NCX. So here n is 50, which will fix. A is this NCX, and this probability power this into other probability power n minus x. We'll just fix these probabilities. So this way we will get the event. I mean, this is 50 here. So these are the different probabilities for 45 heads, 46 heads, 47 heads, and so on. So the sum of all these would give us the probability of uh, more than 45 heads, or greater than or equal to 45 heads in a trial of 50 tosses. So this value in terms of percentages, it is 0.00. Now this value, as low it is, I mean, if this value is low, what does it mean? It means that either of these two statements, there are two statements here. Probability of 45 heads or more given the coin is fair. So now either the coin should not be, I mean, this probability is very less. So since this probability is very less, only one of these two could be true. Either the coin is not fair, or it was not possible to get 45 heads or more. But as per data, we know that 45 heads has come. So the first part cannot be false. It is true. It is already there in the data. So which means that coin is not fair. So this way we are able to reject the null hypothesis and conclude that the alternate hypothesis is true. Now, when can we reject null hypothesis and accept the alternate hypothesis? That depends on uh, what is this p-value. Now, in I mean that the threshold for p-value changes from context to context, but in general, 5% is the cutoff up to which we reject null hypothesis and accept the alternate hypothesis. Now, there could be stricter scenarios where this cutoff could be smaller than this, or it could even be higher than this, let's say 10% and so on. Now, other way of looking at this 5% is that 100 minus 5 is 95, or pardon me. So what does this 5% mean? So up to anything up to 5%, we are accepting that we are going to reject the null hypothesis, which means if it is more than 5%, we believe that anyway this probability of 45 heads or more, if that is more than 5%, we are saying that okay, anyway the probability of that event to happen, even if the coin is fair, is more than 5. So we will go ahead, I mean, we'll believe that coin is fair and there is no reason for it not to be fair. So this 5%, it translates to the confidence with which we are telling a statement. So here, because we are giving up to 5%, we are giving 5% interval, it translates to 95% confidence. So it what we are saying here is that with 95% confidence, we could reject the null hypothesis and thereby accept the alternate hypothesis, which is coin is not fair. Now, why 5%? I mean, although there is liberty in business context to have this number more than this or less than this, there is a reason behind why this 5% is very widely used. A standard normal distribution with a mean equal to 1. In that bell curve, once we have the, I mean, let me try to draw. So in this is how a standard normal distribution works. So here we have the mean in the center, which is mu. So we have for the distribution, we would get the standard deviation as well. So we will have 1 sigma, then uh, 2 standard deviations, 3 standard deviations, and so on. And in the left side, we will have minus 1 sigma, minus 2 sigma, and so on. Minus sigma, minus 2 sigma. Now, if we look at the area under this curve, in 2 sigma, between 2 sigma, minus 2 sigma and plus 2 sigma, the area covered and in this area is, I mean, in this between minus 2 sigma and plus 2 sigma, this area is 95%. So anything outside this plus 2 sigma and minus 2 sigma, this area, the remaining area of under this curve is 5%. So this part and this part. So this is in case of double-sided thing. In case of single side, we would have this area of rejection only in one side. So this is how the so as a standard practice, people usually take minus 2 sigma to plus 2 sigma. So we give the liberty of 2 standard deviations from the mean. And if the value happens to fall between this between 2 standard deviations, then we don't reject the null hypothesis. We give the benefit of doubt to the null hypothesis statement. And in case of very strict things, we even go till minus 3 sigma. So minus 3, if we take minus 3 to plus 3, then the cutoff would be very less because the area under the curve between minus 3 sigma and plus 3 sigma, that's more than, I think, 98 or 99%. I don't remember the exact value. So this is the reason behind why 5% is used as a standard metric. Now, this is a theoretical example where we toss a coin and see how many heads are coming, how many tails are coming, and determine whether it's a fair coin or not. Let's quickly see one small example of practical application of this hypothesis testing in real world. So let me open a new spreadsheet. So let us assume that we are looking into the sales of a particular product, let us say soap, of a particular manufacturer. We have the daily sales of number of soap units sold by this company, by a particular company. Now, the marketing team of this company had come up with a campaign on a particular day promoting their soap in TV advertisements, newspaper advertisements, etc. And the sales of soap had increased on that particular day. And the marketing team claims that that increase is due to the campaign that they had performed. Now, as a CEO, or let's say chief marketing officer of the company, you need to determine whether the increase in sales that had happened on that particular day was actually due to that campaign only, or had it happened by chance. So the claim by the marketing team is that compared to the average in the last 2 months today's sales is high, so that's the result of the campaign. But as you know, the sales of the soap is not going to be a constant number each day. It's going to go up someday, go down someday, etc., etc. Now the increase that has happened on this particular day, whether that is because of the campaign or whether it's just a normal chance, that is something we need to determine statistically by using hypothesis testing. Now let's quickly take an example with some random values. Let's assume we have 90 days of sales numbers. So it is 3 months of sales. Although we will have the actual sales number in real world, for now, let me use random numbers, 100 to 150. So let's assume that these are the number of units of soap sold on each of these days. Okay, and the campaign had happened on the 90th day. Let us assume it to be so. Now let's make it 150 or 160. And the marketing team's claim is that this 160 is more than the average in the previous days, and that is because of the campaign. Now let's see if their claim is true or it's not to be. I mean, it's not the case. So here, the null hypothesis. Let's define the hypothesis first. Null hypothesis is that the campaign had not worked. So it is the responsibility of the marketing team to prove that it had worked. So until it is proven, we will believe that it had not worked. So campaign not worked would be the null hypothesis, and alternate hypothesis, campaign worked. So now let's calculate. I mean, here binomial will not work because it's not a that kind of an event which has only two outcomes with equal probabilities. I mean, with the two outcomes, the probabilities can be different in even in case of binomial, but here it's not an event with more than um, two outcomes. So it could be any discrete number. So here, because we anyway have 90 days of data, let's assume normal distribution. Assume it to be following normal distribution. So the parameters of normal distribution being mean and standard deviation. So we'll calculate the mean, which happens to be 124, and standard deviation, entire population. So we'll use STDP. And the deviation is this. Now let's calculate the probability of this event 160 happening. So norm dist. So the in case of normal distribution, like in case of binomial where the probability is ncx p power x q power n minus x, in case of normal distribution, the formula to calculate the probability is that long formula 1 by sigma root 2 pi e to the power minus x minus mu the whole square by 2 into sigma square, where sigma is standard deviation and mu is the mean. But luckily we have formula in Excel which calculates as the entire thing. Mean is this, and standard deviation we are looking for cumulative. This probability is 0.99. We need 1 minus this to get the area of rejection. This number happens to be 0.8, which is again smaller than 5% if we consider 5 as the threshold. So if I mean, because this is less than 5, we will have to reject the null hypothesis that the campaign did not work, and which means the campaign had actually worked. Now, if we want to test it, instead of 160, let's make it 130. Here, the probability have from whatever it was earlier, when it was 160, it was 0.8. But the moment you make it 130, what happens? The probability happens to be 35%, which means the probability of sales being 130 today, assuming the null hypothesis is true, here the null hypothesis campaign did not work well. So assuming that, I mean, given that the campaign did not work well, the probability of sales being 130 is 35%, and this 35% is a reasonable probability, much more than the 5% cutoff that we have assumed. So we can, I mean, there is no reason to disregard this null hypothesis. So we will stick with this null hypothesis that the campaign did not work. Whereas if the sales is, let's say, 175 or so, clearly the probability of this event, I mean, probability of sales being 175 given the campaign did not work, that probability is very less. So either the sales would have not been 175 or the campaign or this statement would be false. But we know that 175 sales has happened. It is as per data. So the only other possibility is to disregard the null hypothesis, in which in this case the campaign did not work is the null hypothesis. So alternate hypothesis that the campaign worked is to be accepted. So this is about null hypothesis involving normal distribution. The same thing with smaller sample, let us say 20 samples or 30 samples, etc. Would not form a normal distribution, but they usually form a distribution called T distribution. And the probability of an event to calculate the probability of an event in T distribution, the formula is little different from that of normal distribution. It involves sample size and degrees of freedom, etc. But the concept remains the same, like how far this number is from the mean of the distribution. So we could confirm this in one another way. So in very simple way, the mean is this plus 2 times standard deviation gives us this number 155. So anything more than 155, I mean any sales more than 155 is going to have a probability less than this 5%. So that way, I mean, provided this distribution is normal distribution. So here, just by the looks of it, the 2 standard deviation cutoff is 155, and the sales is 175, which is much more than that. So even without calculating the normal distribution probability, we could conclude that the campaign had worked. I mean, it's just a shortcut to see whether the null hypothesis is true or not. So this is about coming back to t distribution. So as I said in the beginning, hypothesis testing is a very generic thing which can be used to test any distribution. We saw example of a binomial distribution and a normal distribution, but even in other cases like uniform distribution or t distribution or Poisson distribution, all we need to do is identify the right formula to calculate the probability of the event happening, and we should assume that that event had happened if the null hypothesis is true, and if that probability happens to be reasonably very small, then we could reject the null hypothesis and accept the alternate hypothesis. Now, a quick follow-up to this hypothesis testing is the errors, type 1 and the type 2 errors. Now, although we are coming up with these probability values and rejecting or accepting the null hypothesis and coming to a final conclusion, etc., we should not forget that at the end of the day, these are all about probabilities only. Even at a 5% confidence interval, even with this 5% cutoff, we are just 95% confident. We are not 100% confident. We are giving ourselves a 5% chances of we going wrong. So there is possibility that we classify incorrectly. So that's where this type 1 and type 2 errors come into picture. So let us say the null hypothesis is actually true and estimated is also true. Then it's fine, it's green. Similarly, if the null hypothesis is to be rejected, it is false, as well as we are also estimating it to be false, then again, it's correct. But if the other two happens, this diagonal cases where the null hypothesis is actually false, but we claim it to be true, if that happens, then that is called a type 1 error. And the other case where the null hypothesis is actually true, but we call it, we reject it unnecessarily, then that is type 2 error. Now, we should see to it that type 1 and type 2 errors are as small as possible. Now, there is a metric called the power of test to measure how effective our hypothesis testing has happened. So, power of test is the probability of rejecting the null hypothesis given that it is false. So if it is actually false and we rejecting it, this green part, that probability is called the power of test, or it is also 1 minus type 2 error, where type 2 error means that it is actually a true case, we are incorrectly rejecting it. So that probability 1 minus that probability also gives us the same probability, which is rejecting H0 null hypothesis, given that null hypothesis is actually false. So that is called power of test. Yeah, so with this comes the end of hypothesis testing. As I said, it has a variety of applications, including practical scenarios like what we saw in terms of determining whether a campaign worked or not, all the way up to even um, things like correlation, regression, etc., where we find whether a particular variable is statistically uh, impacting the other variable or not. So we'll talk about those things tomorrow as to how hypothesis testing is used in deciding what variables to use in a model, or how to prioritize variables. While choosing from a big set of variables, how to prioritize which variables to use, etc. For those in those aspects as well, I mean in those scenarios as well, hypothesis testing would be very useful. We will look into those things tomorrow. I mean with this, I mean let's probably have a quick Q&A session in case of any questions, or we will wrap up with this.
Hi, Om Prakash. Can you able to hear me?
Yes, sir. I'm able to hear you.
Good afternoon. This is Nakiran. I'm a research scholar under Anand Ryan sir, and I'm in MWN lab.
Okay.
I want to make this scenario what you are trying to have been focused with the banking sector, right? You are in regarding
Yeah, yeah.
sales and distributions, right? I'm talking in a different perspective. Whether if the banking sectors has been facing attacks, cyber attacks.
Yeah.
So there will be, I think, every banking sectors will be facing per month at least or 2 or 3 attacks, maybe probably. I'm saying. So how do you make this number of events or samples collected at the network side? How do you make this to be tested with the hypothesis testing? That means you will having a lot of samples that are collected at the network parts, and there are some few events in the month, at least 2 or 3 attacks has been happened. So how do you make this comes into test with hypothesis testing?
So I'm not very sure about it, but the first of all, we need to identify what distribution is very suitable for this scenario. For example, maybe a Poisson distribution might fit, where the number of attacks every month or every day is the event space. And but what are we trying to do is something I'm not clear about. Can you
Yeah,
help
that's
me
only
understand?
I'm
Yeah,
also, because what I used to do means what are
yeah,
the samples, either it is balanced or whether it is unbalanced, we used to make oversampling technique to balance and treat even into machine learning model with our mathematical aspect. So I didn't involve in this kind of testing, whether it is happening at a regular interval or it may be in Poisson distributions. We don't bother about. So we directly feed into machine learning model when we will deal with mathematical aspect. If it is imbalanced, we will make it balanced. So what case I can go for hypothesis testing? If I am talking, I am working in a different domain. I am talking
yeah.
in the banking domain. How do you treat this hypothesis testing in the case of attack scenarios where the data samples are collected at the network part?
I'm not sure about it. Let me also think about it. We could probably talk offline.
Okay, fine.
Yeah, you could
I'll
take my number
explore
from
my.
Sendil Kumar sir. You feel free to call me anytime. We could discuss.
Yes. Fine. Thank
Okay. Probably with this we could wrap this session and reconvene tomorrow. Okay. Thank you all for patient hearing. Thank
I
you.
want
Yeah. Sorry.
a right perspective. What you have been given past one.
I'm sorry, your voice is breaking. I'm not able to hear you. Are you asking something?
Is my question is in the right direction with respect to the data interpretation with the hypothesis testing?
So, can you come again? Again, I'm not able to hear you.
I think I have been problem with my mic. I think so.
Yeah, now I'm able to hear you.
Okay. I want to know whether my question is right direction in the with respect to the today's session.
Um, I'm not sure. That's what I'm not sure. Like I'm just thinking how does this hypothesis testing fit into the phishing attack, etc. that you are talking about. We will discuss together offline.
Okay, fine. Thank you.
Yeah, thank you. Sure. Okay, fine then. Let me drop out.